Okay, so we're up. So I was just kind of announcing to the people that were here what's going to happen with the schedule. Next week is there's an autonomous boat competition that we've let's see, this will be our fourth time competing in. We've won it once, done well the other times. The other times it was in exciting places, like we went twice to Hawaii, and 2 years ago it was in Australia, and this year it's in Sarasota, which is, I guess, still exciting, but doesn't quite have the same feeling as going to Hawaii and all that. So I'm going to be at that competition, so I'm going to put next week's videos on, like I had been doing for Friday's videos. And again, this Friday I'm going to also put it on there, but I'm going to have all next week's videos on the web. Of course, next week on the Friday we have the exam, and the exam goes through Chapter 7. Let's see, other announcements. The week after that is, the Monday is Veterans Day, so we don't have classes on the 11th, and I've been doing the Fridays trying to spend some time with my family and stuff to maintain sanity, and I'm just going to do the Wednesday and Friday that week. So I guess what I'm leading up to is we're going to have 2 weeks of video lectures that are going to be on our website. But for the whole time, I don't want you to feel like I've abandoned you, because if you need to talk or meet about things, if you send me a text message on my phone, I should be able to jump on Zoom right away. I know they gave us at the boat competition, they had real good internet down there. In Australia and Hawaii and places, I expect they'll have good internet at the competition here in Sarasota. And I can just jump on Zoom right away. So again, I won't be standing in class for the next 2 weeks, but I don't want you to feel that you can't get me like immediately if you need to. Let's see. And the other, of course, make sure we're set though, is the only time you'll really need to come to class is going to be on I guess it's the 8th of November, so that'd be a week from Friday is when we have the next exam. And it covers the material through Chapter 7. Okay, so that's all the announcement stuff. Let's see what we have here. I'm going to put this away. That was about the boat competition. And we're working in Chapter 8, and we've done some pretty wild stuff. So let's go ahead and set the big picture again. So as I stroll back to the beginning of these slides, Chapter 8 deals with the Group 2 mechanism. So we're going to have a 3D spatial mechanism whose mobility is 1, and its equivalent spherical mechanism has a mobility of 2. And so because this has a mobility of 1, our problem statement was going to be given all the A's and the alphas for, in this case, 5 links. Given, come on, pen, S5, because there's a revolute, given S1, because there's a revolute, given S3. So I think all the A's, alphas, S1, 3, and 5 are all the constant mechanism parameters that would never change. It's 1 degree of freedom, so we're going to give you one of the joint angles, say theta 5. We should be able to find all the remaining unknowns. So that would be theta 1, 2, 3, 4, and where the cylindric joints are, the joint offsets S2 and S4. And the problem we have with these Group 2 mechanisms is when we go to the equivalent spherical mechanism, it's 2 degree freedom. We know theta 5. So the best I can do is to go to the toolbox we have for that mechanism. I can find an equation that has theta 5, but it's going to have 2 of the other thetas. I can't find one equation, one unknown, like we did in Chapter 7. So it means we're going to have to find an equation that comes from this 3D mechanism that has 2 unknown thetas. I don't care what those thetas are, but if I can get 2 unknown thetas, then I can find an equation from the spherical mechanism in those same 2 thetas, and both of those equations are going to factor into this form here. So one of the unknowns was theta I, the other was theta j, and these terms are all going to be in terms of the constant mechanism parameters in the given theta, so they're going to be numbers. So what we did in the couple of classes ago is we just said, hey, let's not worry about where these equations are coming from, but if we had 2 equations of this kind, how would we find the theta 1 or theta I, theta j pairs that simultaneously satisfy both equations? Turns out there's going to be 8 possibilities, and what we did is we went to tan-half angle and got rid of the sines and cosines, and we turned the equations into these biquadratics, right? Quadratic in x sub I and quadratic in x sub j, where the little a through j's are immediately calculated in terms of the big a through j's, which are known. And then we looked at how to solve that, and that's when we did, Bezout's and Sylvester's methods. Okay, so 8 possible. So I skip down, skip down, skip down. Then we said, how can I go about getting equations from here? And we showed 3 techniques. So the first technique was to take the entire vector loop equation, do a dot product with something. I don't have any strategy at all of what I should dot it with, and I'm not worried about that right now. I'm just saying that if I did that, I will get an equation that has some thetas in it. Maybe I can dot product with something and get an equation that has just 2 unknown thetas. Another one was, which actually not even going to use that one until chapter 9, but was to take the vector loop equation, move some of it to the other side of the equal sign with negatives, and then dot product the left with itself, dot product the right with itself, and boom, you'll get an equation. Again, we don't see any strategy yet of what would I move to the other side, and I'm not worried about that at the moment. And then this is the wild one, this secondary cosine laws. So that's when we got into this discussion about dual numbers, and we saw how to add, subtract, multiply, divide, and then we said, what if I had a function of one variable? And here's the Taylor series expansion. If my expansion point was a, and I tweaked it by delta x, and again, with Taylor series expansion, there's an infinite number of terms to get the exact answer. But because epsilon squared is 0, when we apply this to a dual number, all those higher order terms, the delta x's, the epsilon a naught, they all went to 0, and it's not an approximation at all. So that's kind of wonderful. Then we said, what if I had a function of more than one variable? So right now I've got 2 variables, some function of x and y. And I'm going to say my expansion point, x equals a, y equals b, and I'm going to tweak it in the x by delta x. I'm going to tweak it in the y. This is the entire Taylor series expansion where it has to go for an infinity of terms. Basically, it's saying that the function that's tweaked a little bit from the expansion point ab is going to be about to the function at ab, and then it's the derivative in the x times how far you tweaked it in the x, and that derivative has to be evaluated at the expansion point. And then it's the derivative, the slope really, in the y direction, evaluated at the expansion point, times how far you tweaked it in the y plus these terms. Well, we tweaked it in the x by that, tweaked it in the y by that, so all those terms went to 0, so it's not an approximation. And again, if we had a function of 3 variables, like x, y, and z, then I would have to say, I'd have an extra epsilon. I'm going to say I put in c plus epsilon c naught. So I had epsilon c naught, the partial with respect to z, evaluated at x equals a, y equals b, z equals c, and again, if you had 4 variables. So it's a bit of a bookkeeping problem, but it's not terrible. Okay, then we got into this idea of dual angles. We said, let's define, for example, theta 1 hat as this, epsilon s1. And we're going to define, for example, alpha 2, 3 hat as alpha 2, 3 plus epsilon a2, 3. And these dual angles are pretty neat because that dual angle alpha 2, 3 tells me everything I needed to know about link a2, 3, right? Link a2, 3's job is to maintain the relationship between the lines s2 and s3, and that relationship is defined by the perpendicular distance a2, 3 and the twist angle alpha 2, 3. And that theta 1 hat tells me everything about the joint along S1 because the joint is defined by the joint angle theta 1 and the joint offset S1. So those are kind of neat dual angles that they do that. And then we made this wild statement last time where Kotelnikov, a fellow from Russia, came out and proved, but it was very difficult to follow, especially if you don't speak Russian, that if you took dual angles and put them into any of our cosine laws, or any of the equations actually, but I keep going cosine laws because they have 1 less theta. If you put dual angles in there, you're going to get valid results, and that's what we're going to be looking at today. And we put those dual angles into those cosine laws. We call them secondary cosine laws. Okay, before we do that, I went ahead and wrote a little thing up here. I kind of want to show that if I put dual angles, say, into any of these trig identities that we're used to, they better be valid because there's a relationship that is supposed to be true. So what if I had this function x and it was equal to this cosine squared? And I'm going to go ahead and put that dual angle like theta 1 hat. I'm going to put theta 1 plus epsilon s1. So according to our expansion, it said, oh, you know, from our Taylor series expansion, that's my expansion point, and I tweaked it by that much. So the value of the function at that is going to be close to the value at the expansion point plus how far I tweaked it times the derivative of the function evaluated at the expansion point. Okay, so here's this. And then here's how far I tweaked it. And then the derivative of cosine squared is going to be 2 cosine times negative sine. It's like that chain rule thing. So it was 2 cosine, and then they take the derivative, you know, the negative came into it from that. So I said, okay. So I put, so we haven't done anything magic here. We just took a function of one variable, and we plugged in the dual angle and evaluated it. Now I'm going to say I got another function, g, and it's going to be sine squared. And basically, we're going to add those two together and hope we get 1. So here we go. I plug this in. So the value of the function at this is going to be close to the value of the function at the expansion point, plus how far I tweaked it, times the derivative with respect to x evaluated at the expansion point. So here's that. Here's how far we tweaked it. And then the derivative of this is going to be 2 sine x times cosine x evaluated at x equals theta 1. So we get that. And kind of lo and behold, when we add these together, so here's where I put that dual angle into that function and added them together, and I get that squared plus that squared. And those cancel. So I wound up with 1 plus, you know, 0 epsilon. So in a way, by doing this one, I said, wow, that's kind of neat. All the trig identities are going to work, are going to still be valid when we put dual angles in. It makes me kind of feel not quite as crazy about putting them into the cosine laws, and they're still going to be valid. But then we did show in the notes page, there was a paper that Dr. Duffy did with Jose Rico to, you know, sort of explain Kotelnikov's thing. But even that paper, even though it's not in Russian, is pretty deep. So I'm going to say, yeah, okay, fine. So let's go ahead and put dual angles into a cosine law. So again, we are going to want to solve that 5-sided thing that was at the start of this. I was trying to clear my screen, and it did something to me here. Here we go. You know, we are going to want to solve that 5 bar that was out there that was group 2, but let's just start with this and say that I know for this quadrilateral where one link is fixed to ground, that it turns out this one is a 1 degree of freedom thing, but it doesn't matter right now. I know that's a valid equation, Z41 equals C23. So we're going to want to go ahead and just for practice put dual angles into that and see what we get, see what we generate. So again, it doesn't help solve the problem that we're going to be doing, that 5 bar, but it's what we're going to start with. So I'm going to take Z41 equals C23. And let's see, I'm trying to remember all the notations and stuff that he used. We're going to go ahead and put all the dual angles in. We're going to start with the right-hand side because the right-hand side is a function of one parameter, right? It's the cosine of alpha 23. And what we're going to do on the right-hand side is we are going to substitute alpha 23 hat. It's the cosine of alpha 23 plus epsilon A23. So that's what, on the right-hand side, it's pretty easy because it's a function of one variable. Okay, so for the right-hand side, and then we're going to put, you know, dual angles in here and expand that and equate the two. So on the right-hand side, let's see. I could say it's a function of x, you know, is cosine of x, and I want to evaluate it at alpha 23 plus epsilon A23. So it's going to be equal to the function evaluated at alpha 23 plus how far we, I call it tweaked it, that's like our delta x, times the derivative, oh, let's go ahead and write it down. You know, it's the derivative of the function evaluated at the expansion point, times how far we tweaked it. Okay, so what's that derivative evaluated at the expansion point? It's going to be, see, the derivative is negative sine x evaluated at alpha 23. So that's going to be negative sine of alpha 23, which I'll just write as negative S23. Oh, the function evaluated at 2, 3 is just, again, the cosine of alpha 2, 3. Oh, okay. So when we looked at the right-hand side, it was an easy one because it was a function of one variable. And yeah, that's what we get. It's got a real part and it's got a dual part. Okay, I'm going to get rid of the parentheses. I'm going to write it as negative, what do we have, A23, S23? Hopefully times epsilon. So you can see the real part and the dual part. Hopefully I didn't mess that up when I erased it and wrote it down again. Now the left-hand side is going to be more complicated because this is a function, it turns out, of 5 terms. I know it's got theta 4 in it, I know it's got theta 1 in it, and from doing this for however many years, I know it has alpha 3, 4, alpha 4, 1, and alpha 1, 2. So it is a function of 5 variables. So I'm going to have to use this whole board here. Actually, I didn't even get coffee today. As I'm doing my travels, I had some milk at home, and if I don't use it up, it's going to go bad. So, but I'm going to pretend that that's giving me extra energy. Okay, so we could write it like this, Z41, and just put a hat over the top, and I wanted to peek in the book and see, does he ever? Yeah, we use that notation in places. So this is, it's a function of, holy cow, theta 4, theta 1, alpha 3, 4, alpha 4, 1, and alpha 1, 2. Holy cow. Okay. And we are going to substitute, and this is what's kind of weird now. It's a function of those. And guess what we're going to do? We're going to put theta 4 plus epsilon S4. So what's kind of strange is this name and that name are the same, and we didn't have that even, because last time I called it cosine X, so the names weren't the same. And that just makes it more confusing, but it's okay. And here we're going to put, you know, theta 1 plus epsilon S1, and here we're going to put alpha 3, 4 plus epsilon A3, 4. And then here we're going to put alpha 4, 1 plus, oh my goodness, that Kotelnikov guy, man, he got us. It's kind of neat that we get these equations, but boy, there's a lot of work, and I hate doing these partials, but let's just do it. Let's see what we get. So I had this function of 5 things. I'm going to substitute all these dual angles. Okay, so when we put the dual angles in, I'm going to get the function evaluated at, right, the first part, right? Because it's just like the function evaluated at the what, I call that the expansion point. Well, when I put theta 4 back in there for theta 4 or whatever, I mean, that part's just going to wind up being Z41 again. The real part isn't going to change. It's just kind of funky because the name of my expansion point was the name of the variable. It looks weird, but that's what's going to happen to the real part. So nothing really changes there. Okay, what about the epsilon part? Oh my goodness. It's how far I tweaked it. So it's going to be epsilon. Oh, I already got the epsilon. I pulled it out here. It's going to be S4 times the partial of Z41 with respect to theta 4. You know, before it was, when we had x and y, it was the partial with respect to x and at the expansion point. So I write the partial, and then I say, I got to evaluate that at the expansion point, and it's so weird. Theta 4 equals theta 4. It was easier when I had different names. In other words, if this name was different than that, it kind of was easier to write down. And oh, and then the expansion point, my theta 1, my expansion point was theta 1. And then the variable alpha 3, 4, evaluated at the expansion point, it was called alpha 3, 4. And the variable alpha, holy cow. So what I usually wind up doing is, because those names are all the same, I usually don't even write them down. So it seems pretty funky what's happening there with the notation. Okay, then I've got to go S1 times partial Z41 with respect to theta 1. And then I'm going to have this expansion, or how far we tweaked it, A34, because again, I pulled the epsilon out front. And it's going to be the partial of Z41 with respect to alpha 34. And then it's going to be this one. I tweaked it epsilon A41, and then it's the partial with respect to 41. And again, it's evaluated at the expansion point, but the expansion point names are the same names as the variables, so that I can just leave it like that. But it does drive me nuts that that's the case. Partial Z41 with respect to alpha 1, 2. Okay, so if we go to the right-hand side was cosine 2, 3. It was an easy one, a function of one variable. We had a real part and we had a dual part. What we're going to do is over here is when I put in the dual angles, I'm going to have a real part and a dual part. When I equate the real part, I don't get anything new. But when I equate the dual part, that's what's new. So when I take this negative da-da-da, and we're going to have to evaluate all of these partials. If I take the stuff that was multiplied by epsilon from the right-hand side of that equation and equate it to the stuff times epsilon from this side, that's what we call the secondary cosine law. It's the stuff when you put dual angles into these expressions. If I take, because I got something equals something in my original toolbox equation, and when I put all those dual angles in, whatever's multiplied epsilon on one side, I equate it to what was times epsilon on the other side, and that is the secondary cosine law. So we have to do these partials. So usually when I do secondary cosine law, I just write this down, and then I write, I figured out the dual part on that side, and I just equate them. I don't write all this other part, because you don't get anything new from the functions evaluated at the expansion point where the variable names happen. Oh my goodness, they happen to have the same names. Okay, so we need to get these partials. So I'm going to take the Z41 equation, or definition, and I always have to stop for a minute. What is it? Sine 1, 2, no bar, xs plus yc plus a cosine z. Okay. And I look at that, and I know I need those 5 partials, and I'm looking at it and saying, are there any easy ones to get? And the first one I look at is the alpha 1, 2. Oh, that's going to be an easy one. Right? So the partial of Z41 with respect to, because there's no alpha 1, 2 in those expressions, so when I do these partials, let's see, I'm going to get sine goes to cosine. Cosine goes to negative sine. And then I say, oh, wow, I got a name for that. Oh, I got something wrong here. 4, 2. Oh, my goodness. 1, 1. I don't know how I got onto that. It's because I got milk instead of coffee. So the name of that, oh, it's got a name, Y41. So I can go over here and say, Y41. So that was an easy one. So I guess I know I got to do 5 partials. It turns out that 4 of them are going to be pretty easy, and the other one's a little bit more work. And the way we're going to do it on the board today is better than what's in the book. I don't know why. Well, I know why I did it that way, because they did a paper that did it that way. But what's in the book isn't as clear as this. Okay. What's another easy one? Theta 1. Theta 1. Because the only place theta 1 is going to appear is right there. So that partial is going to be easy. All right, because I'm going to have S12. I'm going to get x cosine minus yc. Oh, I got a name for that. Okay, so the theta 1 partial was not bad. I'm going to erase this. X41 times S12. So that wasn't bad. And then you start looking at some of the other ones and you're like, oh my goodness, right? Because if I need to get, for example, theta 4, and then this is where the book, I don't like the way the book did it. It would be S12, wow, theta 4 is in there. It'd be that partial with respect to theta 4 times S1. plus this partial with respect to theta 4 times cosine 1 plus C12 times that partial. I mean, that's what it's going to be, because I don't see the theta 4 staring at me, so I got to go at it like that. And then I'd have to expand these definitions, and, well, we're going to do something a little bit different. I'm going to say, you know, by definition, Z41 is the same as Z14. So the partial with respect to theta 4 has to be the same as the partial of 1,4 with respect to theta 4. So I'm going to expand Z14's definition and take that partial, because theta 4 is going to pop right out. Okay, Z14's definition is what, 3, 4. And I do have to put the bars now. XS plus Y1 bar C plus C12 Z1 bar. And the partial of Z14 with respect to theta 4 is pretty easy now. Wait. Sine. It's sine 3, 4, and then the sine's going to go to a cosine, a cosine negative sine, XC, oh, I got a name for that. It's X14. So we got that one. So it wasn't that bad. S34, X14. Okay, another one that's going to be easy from Z14's definition is this partial, right? The alpha 3, 4, because it's staring right at us. So when I do that partial, I'm going to get a cosine and a negative sine, and oh, I got a name for that. That's Y14. But there's one term, there's always one term that's kind of difficult, and it's the alpha 4 1 term, because it's not helping me on either one of these. So we are going to have to do it the long way for that last term. So the partial of Z41 with respect to alpha 41 is going to be S12 times the partial of X4 with respect to alpha 41 plus times S1, the partial of X4, Y4 with respect to alpha 41 times C1 plus C12. So yeah, it's a pain. Because now I got to expand X4's definition. Okay, that's S34, S4. Hey, there's no alpha 4, 1 in there. So the partial, okay, well, okay. That was kind of nice. That was 0. But we do have to do Y4 now and Z4. So let's write down those. And again, I don't have any magic here, right? This is like brute force of the sledgehammer, you know, and it's not much fun either, and it's easy to make a mistake. But if you don't make a mistake, you get the right. So what's that? Negative SC plus CSC. So it's a 4. We're going uphill, so I get the 3, 4 before I get to 4, 1. So the partial of Y4 with respect to alpha 4, 1 is negative. Let's see, that sine goes to a cosine. I got to be careful with my negative, that because this cosine goes to a negative sine, and the negative and negative, I'm going to put a parenthesis. I think I got it right. I got a negative CC minus SSC. It looks like negative Z4. If I didn't make a mistake, and yeah. So that guy comes in as a minus Z4. And then we got to take Z4's definition, and I hope I didn't mess that up, and write it out, and then take its partial and plug it in there. So Z4's definition is CC minus SSC. So I get a 4 and a 3, 4 and a 4, 1. And I go partial Z4 with respect to alpha 4, 1. Okay, so that goes to a negative sine. That goes to a positive cosine. I'm going to pull the negative out here. So I got a negative SC plus CSC. Isn't that Y4? Is that right? I hope I haven't messed this up. So now, this term, which is right there, looks like it is going to be negative S12Z4 times C1. Okay. Plus, oh, with a minus, C1. Right, so all of that was that term. So according to Kotelnikov, a legal equation is going to be when I take all the stuff that's times epsilon, when we put dual angles into this thing that was a function of 5 variables, and I equate it to the right-hand side of the equation where we put dual angles in for alpha 2, 3, and we equate the dual parts. A legal equation is going to be this offset distance times sine alpha 3, 4, x14 plus that distance times that plus a34 times that plus a41 times that plus a12 times that is going to equal negative a23 s23. I hope it does. It does, due to their proof. And again, Dr. Duffy, they wrote that paper to go through that proof again, but it's kind of deep, so I am hand waving, on that part. But boy, it's a little tedious. And the way that we wrote this is so much nicer, I think, than the way it was written in the book. Because it's just, here are those 5 terms. I've got to evaluate these 5 partials. And it is weird that, because normally you say I have to get that slope in that direction evaluated at the expansion point, but the expansion point names are the same as the XYZ names. So I didn't bother to write that part down. Okay, 905. So we did one example. We are going to go back and try to look at a strategy now of how in heck do we solve one of these group 2s. See if there's anything I left out. Oh, okay. I'm looking at equation 8.77 and just seeing if I messed up. Minus S on that one term. Looks like that was supposed to be a plus sign, so somehow I messed that up. So I got something on the board that looks a little funky. Okay, but let's look at how we're going to attack this mechanism. So when we did the chapter 7 stuff, we knew that we were going to be able to find one equation, one unknown in the toolbox. And we had a strategy then. It's like, well, which unknown did I want to go for first? And then go in the toolbox and find that equation. So we need to come up with a strategy for these group 2s. So the strategy to me is the most important part of the whole chapter, right? And that's what we're about to do. So that's why I'm being dramatic and checking the clock and seeing how much of the story I can get out, because then a whole bunch of the story is just going to be me sitting at my desk up in Alabama talking to the computer. Okay, so the one we're trying to solve, I'm going to draw the planar representation of the 3D spatial mechanism. 5, 4, 3, 2, 1. We've got a revolute. I believe it's cylindric, and revolute. So hopefully that's the one that we've been doing a whole ton. Okay. Oh, well, let me show the PowerPoint for a minute, because I got the planar representation up there, but the picture is so much nicer on the 3D. And what I really liked on it was up in the red up there, in the pen stuff, I wrote down what are we given, what are we looking for. I should write it on the board too, it is important. Alpha 1, 2 through alpha 5, 1, A12. And again, it depended on which way you pointed your S and your A vectors, but okay. Once we've got those labeled, and it looks like I did not label the A vectors, okay, you would know those values. The other constant mechanism parameters was there's a revolute joint at 1, 3, and 5. So I'm going to know those offsets. And that's it. It's a 1 degree of freedom spatial mechanism, because if I take the sum of the freedoms of the joints, I get 7 minus 6 is 1. So we're going to give you one piece of information. And what do we have to find? Well, there's all of these angles, and then where the cylindrics are. And what we're going to find is there could be up to 8 solutions. This one's a little bit special, though. There's actually only going to be 4 solutions, but that's okay. So all I know is I need to go to this 3D mechanism. And again, this thing on the board doesn't look as pretty as the 3D one that's out there. And all I know is I need to find an equation. It's okay to have theta 5. It's okay to have 2 of those thetas, and I don't care one hoot which 2 they are. I don't care. I just got to find one. But I also look at this, and I look at these guys and say, I can, and that's what's going to be our strategy. That's what's going to drive us. I don't want those offsets when I come up with an equation here, because there's no way from the spherical mechanism I'm going to get those unknowns, you know, because they're not in the spherical equations. So that's our guiding strategy. I don't care what 2 thetas they are, but boy, I need an equation that's not going to have S2 and S4. So I look at our strategy. We talked about 3 things. We're only going to worry about 2 of them right now. Take the vector loop and do a dot product, or a secondary cosine law. Okay, dot product to me sounds easier. So I take a look at it and say, is there anything I could take the entire vector loop that has 10 terms in it, right? 5 S vectors and 5 A vectors. Is there any thing I could dot product those 10 terms with where those would fall out? So I need to do a dot product with something that's simultaneously perpendicular to 2 and 4. And there's nothing easy. I guess I could try to cross 2 and 4 and dot product on that, but holy cow. You know, if these cylindrics were next to each other, which is like the one we're going to do next class, I would have taken the vector loop and dotted it on A23, because I know I would not get those offsets associated with the cylindrics, but they're not next to each other, so I don't see a way to do the dot product. So then it comes down to, is there a cosine law then that I'm going to put dual angles in that won't give me that? If I pick a cosine law that has theta 2 in it, I'm going to have this term, whatever the thing is with respect to theta 2. And if I have a cosine law that has theta 4 in it and I put dual angles in, I'm going to get that S4. So I got to find a cosine law that does not have 2 and 4. And I'm going to put dual angles in and pray that it has just 2 unknown thetas. I'm not guaranteed, I don't know ahead of time if that's going to happen. So there's only one equation that jumps at us for this problem, and it's this one. Z51 equals Z3. I'm going to put dual angles into that. And I'm just saying we only got about 9 minutes left, and I got to do a whole bunch of partials. Ugh. But that's the strategy. So that's like the super important part of the whole thing today. Why did we decide to attack this problem in this way? It's because I know I will get an equation that won't have those guys in it, because holy cow, I know I'm only going to get thetas. I hope, well, it's okay. I know it's going to have theta 5, but that's given. I hope it has only 2 of the thetas in there. I'm not really guaranteed, maybe off the bat, but it seems to be the only plan of attack. Yeah. Mm-hmm. Oh, there was something I was supposed to show on the other one that I forgot, but I erased it. That's okay. We'll get to it this time. So we're going to put dual angles in that. We're going to say in other words, Z51 hat, and oh, here's some of the other notation. The real part and the dual part, we call it Z051. So that Z051 is all the stuff multiplied by epsilon. On the other side, when we put dual angles into that, we're going to get the real part plus epsilon. We call that Z03. So the secondary cosine law is going to be Z051 equals Z03. And we kind of hope it has 2 thetas in it. Okay, so let's do the Z3 one. So I'm going to say Z03, when I put what's going to be in the dual part, I know it has theta 3 and it has two alphas, so alpha 2, 3 and alpha 3, 4. So I know it's going to be S3 times the partial of Z3 with respect to theta 3 plus alpha 2, 3. So this is where I start, like, I don't want to call it taking shortcuts, but I'm like, I just care about the stuff multiplied by epsilon. So I'm just going for that. Let's see, there's one term left, A3, 4. Okay, so Z3's definition is CC minus SSC. I'll try not to make a minus sign mistake. Let's see, what do we got here? 2, 3, 3, 4. Okay, so this partial with respect to theta 3 is going to be S3, 4, S2, 3, S3. Because the derivative or the partial, that went to negative sine 3, and the negative there gave me a positive. Okay, this partial with respect to S2, 3, I'm sorry, with alpha 2, 3, is going to be, that cosine, I'm going to get a negative SC. If I pull the negative out front, plus CSC, let's see if I got this right, SC. Does it have a bar or not here? With respect to 2, 3. Oh, yeah. So I think that one's that partial if I'm trying to do it all right in my head and everything. That came out to minus Y3 bar. And then when we do this partial with respect to alpha 3, 4, right, that goes to a negative sine and a positive cosine. So if I pull the negative, I get a negative. Oh, the negative, that's where I lost my minus sign before, I guess, right? The definition of Y3 has the negative, right? Negative, so that's where I messed up on the last one. Okay, so it looks like this one went to Y3. So, yeah, painful. We got 5 minutes left, and we got the larger one left, the Z5 term. Because that has, well, just like the last one we did, it has 5 terms. So I'm going to say Z051 is equal to, let's see, it had theta 1 in it, so it's going to have S1 partial with respect to theta 1, and it had S5, so the partial with respect to theta 5, and it had A45, so it's the partial with respect to alpha 4, 5. And it had A51. That's going to be the difficult term. And then it had A12. We got 5 minutes to get to a happy ending spot. Okay, Z51's definition. It's like, oh man, there's no magic here, but it's going to be a sine X S plus Y C plus a cosine Z. Again, that's going to be an easy partial because the theta 1 is staring at us. Oh, wow, that's going to go to S12 XC minus Y. Isn't that X51? The alpha 12 partial is going to be easy. It's going to have a cosine negative sine. Wow, that's Y51. For these other two, I'm going to go ahead and expand Z15. Take the partials. And the thing that I forgot to show is, I mean, it's not that hard, right? Z15, take those partials. But boy, you know what we're going to get? I call it, in the book, it talks about this cyclic exchange of subscripts. I know that, and this is how I had to memorize this, or you don't have to. You can take Z15's definition, take the partials. We got 3 minutes left to tell this story. I looked at that and I said, wow, 5, 1, 2, 3, 4, and it, 5, 1 went to 1, 5, right? Z15 is, this again, I'm just coming up with a stupid way to remember this. 1, 5, 4, 3, 2. If I change subscripts, I am going to get, so what I mean by that is, if I look at this term, 1 went to 5, yep, so I'm going to get this term. S12 goes to S54. Well, I don't have 5,4, but I have a 4,5. X51, X15. So that gets me this term, which I could have gotten from Z15's definition. And the other term that's going to pop out is this one, because 4,5 goes to 2,1. Well, yeah. Oh, I'm sorry. 1,2 goes to 5,4, but I don't have an A5. I got a 4,5. Okay. So this partial says if I take this and I do that cyclic exchange, I'm going to get that. Or, so what happened is I would have taken the Z15, expanded it, and done those two partials. And then when I looked at the results, I said, wow, I could have done that cyclic exchange on those other terms and gotten them also. So whichever way works for you is fine. There's always one term, though, that's a pain. So that term, we got 2 minutes left, is when we do the partial with respect to 5,1. So I'm going to have to sneak this part out here. I can get rid of that. It's going to be this partial with respect to alpha 5,1 and this partial. So we have to brute force it out. So we'll have to expand those. Oh, this X5 doesn't have alpha 5,1 in it. And again, we have to expand the definitions of Y5 and Z5. And let me see if I just have the result of that. Did we? Oh, again, I don't like the way you did it in the book. I think it's clear what we did here. Dang it. And we're out of time. Okay, when we do this, though, it's not that hard. I forgot what it comes out, but it's going to have theta 5 in it, right? It's not going to have any other thetas, and I don't care what alphas are in there because I know them all, and that's going to have theta 5. So if we take the Z03, that's when we put dual angles into Z3, and we only looked at the stuff times epsilon, and we looked at it and said, boy, I hope I get an equation that has only two unknowns in it. I got theta 3, I got theta 3, I got theta 3, got theta 5 and theta 1. Okay, so it looks like 1 and 3. 1 again, I got 5 is given. 1. 1. In this one, again, these, 1. Hey, it looks like the secondary cosine law gave us an equation that had theta 1 and theta 1 and 3 as the unknowns. So again, our strategy was, I can't see anything to dot product to get rid of those offset terms. So I said, I'm going to have to go to a secondary cosine law. I knew I needed to get a cosine law that did not have theta 2 and theta 4, because if I did, the secondary part's going to have those unknowns. I just can't deal with those at the moment. So our only choice was this, Z51 equals Z3, to put dual angles in. And when we fought through the dual angles, we got an equation that had the given theta 5, it had theta 1 and theta 3 in it. That is going to factor into the format that we talked about at the very beginning of this chapter. And we are going to pair it with, in this case, we're going to pair it with that equation. There's an equation that has 1 and 3. This is the only mechanism I've seen where the equation that I pair it with is the same. This is the only case of the mechanism I've seen where the equation we pair it with happens to be the equation that we put the dual angles in. That usually doesn't happen. But for this one, so what I'm going to do on the video part is kind of try to pick up from here and just wrap up any little stories on the end of this. But the most important thing was over here. When we looked at it, it said, I know I need to get from the 3D mechanism an equation that has two unknowns. I have no idea. I don't care what the two unknowns thetas are. But boy, that equation better not have those. So that's our strategy. That's our whole driving force. And it looked like if I took that cosine law and put dual angles in, at least I won't get those unknowns. I don't know what I'm going to get, but okay, so that's the strategy. So at least we have a strategy for this. But boy, it's a lot of work, because once you get those two equations, right, you get the whole Bezout's thing and that you have to deal with. Okay, so I got boat competition next week. Then we have Veterans Day, and I'm just going to avoid 5.5-hour drive each way that week. So there'll be a little bit where I'll be on the road. So the one time, though, you want to come into the room is the 8th for the exam. Look at the old exams that are out there. If it's not going to hurt the people that are in the off-campus section, you know, boom, you get the exam sent to you. There's always some people that are in the big section that are on travel and things, and it's not going to hurt if you send, so I'm kind of talking to the people that are not here, is to send me a Canvas thing to remind me that, hey, I'm still need to be off campus and that because I'm still doing something, just to confirm that I don't mess you up on that. Okay, so we'll see you, and actually I'll physically see you in a couple weeks.